Okay, today's topic is shock boundary layer interaction. We know what shock waves are, and we also know what boundary layers are on a flat plate or other surfaces. Now, when a shock wave comes in close proximity of a boundary layer and interacts with it, it results in some fairly complex flow pattern, which is quite challenging for computational fluid dynamics to predict. And it also happens to be quite relevant practically in many scenarios, so we need to learn how to handle them well. Today's lecture is part 1, where we will look at the simplest geometry which can generate a shock boundary interaction, and that is the compression corner flow. Okay. The geometry of a compression corner is very simple. We have a flat plate, and at some point it is bent upward. The bent part of it is called a ramp, and the corner is where we will focus our study. So it's a compression corner, or also called a compression ramp. We have supersonic flow or hypersonic flow coming from the left. When it encounters the deflection, it generates a shock wave. If the deflection of the surface of the plate is theta, we can find the shock angle beta by inviscid theta beta m relation for oblique shocks. We can also compute the pressure rise across the shock wave from inviscid theory, and let's say we want to plot it as a function of x. Before the corner, which is here, we have constant pressure. Let's call it P1. At the corner, we have a sudden jump because of the shock wave to a value P2. Okay. Now, where do we encounter such compression corners? One of the most common example is a control surface. Think of a flap which is deflected, and the flow going over the wing has to turn and generate a shock wave. The pressure rise that we obtain across the shock is actually what helps us to generate the extra control force. So here we are interested in generating extra force for the aircraft. Another scenario where we commonly encounter such compression corner flows is in engine intakes, and there high-speed engine intakes, air-breathing engine intakes, where shock waves of such kind are used to increase the pressure and density and temperature of the gas, essentially to achieve compression for the engine. We will see subsequently how presence of a boundary layer will alter the pressure distribution, which will have an effect on either the force generated by control surface or the compression, or vice versa. Okay, now this is the inviscid picture. Let's now add a boundary layer. The inviscid picture is such that you can imagine that there is no boundary layer, hypothetical, or even if there's a boundary layer, it's very thin, so that it does not make a difference to the shock wave. But in most scenarios, that is not true. So here comes the effect of boundary layer. Let's draw the same picture again. A plate, a ramp, now we will plot a boundary layer profile. Coming from the left, Mach number is again greater than 1, at least at the edge of the boundary layer. When the boundary layer encounters the shock wave, it is an adverse pressure gradient because pressure is increasing across the shock, and the higher pressure tries to push the flow backward. In fact, what we encounter in many situations is that the boundary layer will separate. There will be reversed flow generated near the corner. Let me draw it as this shaded region. Let's look at a magnified view of this reversed flow. The flow coming from left, and in the reversed flow is going backward, and there's a point which is called the separation point in between, where the flow will have to turn to match up with the outer flow that goes over the bubble, and the opposite happens at the other end of the separation bubble, as it is called. So the flow goes over it and then what's called reattaches and flows along the ramp. So the first thing that we see when we have boundary layer is separation, as it's called, a bubble. It's like a vortex, and in which the flow is separated and is recirculating. For that, we have a separation point where velocity on the left, flow is coming from the left. On the right, the flow is coming backward, and that point is like a small stagnation point. And there's a retachment point, similarly, where the flow goes back on the ramp. At the separation point, the supersonic flow coming from the left has to turn abruptly over this obstacle, which is now the separation bubble. So it will actually generate a shock wave. And that shock wave actually curves, kind of curves downward. Then the flow goes over it, over the separation bubble, and then again it has to turn back on the ramp, where another shock is generated, and these two shocks meet and generate a third shock. Let me show the shocks by a darker line to make the point more clear. So now, in addition to separation bubble, we have a separation shock, we have a reattachment shock, now what in the inviscid scenario we only had a single oblique shock. Now we have, in effect, a separation shock and a reattachment shock, and a third shock which is formed at the intersection, and the outer shock kind of resembles the inviscid shock wave that we have drawn in the earlier picture. The recirculation bubble happens to be recirculation bubble acts as a extra blockage to the flow, as if the surface has moved up and the outer flow has to go over it. So now, how does this affect the pressure distribution on the surface? Let's look at that. Once again, let me draw pressure along x-axis, pressure along the surface, and let's say we have a point, this is the location S, and somewhere here, well, let's start with S first. Before S, the flow is undisturbed, pressure is P1, and let's say the corner is somewhere here. So the inviscid pressure rise would be what we had seen before. But now we have a shock wave at point S, so there will be a pressure rise, something of this sort. And then there will be another pressure rise on the ramp, and then it will reach the final inviscid pressure P2. The reattachment point is somewhere in the middle of the second pressure rise. So first one is a separation shock pressure rise, reattachment pressure rise, and in between the two, the flat region in between the two represents the separation bubble between S and R, separation and reattachment point. There we get a pressure plateau, as if it's a hill and there's a flat part which is the pressure plateau. Separation bubble has relatively uniform pressure along in that region. Now, if we are interested in the force generated by the ramp or the deflected part of the plate, which can represent a control surface, now the pressure which was expected to be the dashed line inviscid has altered quite a bit to give a different kind of profile. In fact, part of this ramp is actually at a lower pressure than the expected inviscid value. So the net force generated by the control surface can actually be lower than what it is designed for, based on if you are doing only inviscid theory. So let me write that S shock boundary layer interaction, SBLI is commonly called, can alter control forces. Okay, now let's look at another aspect of this interaction when we plot the skin friction coefficient along the plate and the ramp. The plot looks like something like this. Here I have skin friction coefficient CF on the y-axis, and along the x-axis, x is the distance along the x-axis, but I'm going to plot x-axis somewhere in the middle. 0 is somewhere here. Okay. Surface, the point S and point R, let's put them for reference. Before separation, we have a normal boundary layer attached on the surface on the plate. Skin friction coefficient is fairly constant, and we plot it, let's say here. At the separation point, skin friction coefficient will dip quite abruptly and be negative for a region up to the reattachment point, and then rise to a much higher value than it started off with, and kind of be at that level, higher level. So to note CF less than 0 in recirculation region, and why that happens can be understood in terms of the velocity profile. Before the separation point, the velocity profile is of a normal boundary layer. Flow velocity is 0 at the wall, and then it's positive as we go away from the wall. Du dy, derivative of velocity with respect to y, is positive. Shear stress is positive, and skin friction coefficient is positive. As soon as we cross the separation point, flow is going backward. So if you have to compute the velocity derivative, du dy at the wall, starting from 0 velocity at the wall, right next to it we have a negative velocity, so this becomes negative as whenever we have a reversed flow, and we get negative negative shear stress, negative skin friction coefficient. The opposite happens at the reattachment point. Flow is going negative on the left, and as soon as the flow reattaches, the flow is going towards the right, positive x direction, velocity is positive, derivative is positive, and skin friction is coefficient is positive. The other thing to note, so skin friction coefficient changes sign once at the separation point and another time at the attachment point. The other point to note is that starting with the value of skin friction coefficient of the undisturbed boundary layer, it goes through this crazy format pattern near the corner. Remember that corner is somewhere here. And then goes on to a higher value, a higher CF on ramp after reattachment. So if you're concerned about drag, you will probably increase the drag because of this interaction, because of the shock bound interaction. Skin friction coefficient also goes hand in hand with heat transfer. If you study the heat transfer aspect of it, which we will not go into much, but I would like to point out the heat transfer plot will also have a very similar pattern. It will start with this undisturbed value at in the boundary layer before the interaction, decrease in the separation bubble, and then increase to a high value after the reattachment point. In fact, high heat transfer to the surface at or near reattachment point is actually a major concern in many of these shock bound interaction flows. So just to recap quickly, we have a shock wave generated by a compression ramp or a compression corner. The boundary layer cannot negotiate, cannot overcome the adverse pressure gradient of the shock wave. It separates to form a separation bubble. At separation point, it generates an additional shock wave, and a reattachment point is a third shock wave. And the separation and reattachment shocks have their own pressure rise. So instead of seeing one single oblique shock pressure rise at the corner, we see two pressure rise in a shock boundary layer interaction. And in between the separation and detachment point, we have a pressure plateau, which represents the separation bubble. This is where we have negative skin friction coefficient as plotted here, and after reattachment, the skin friction coefficient and surface heat flux to the surface from the flow, if the flow is hot, which is usually the case in a high-speed flow. Heat transfer to the wall attains a peak value, a high value, which can be a concern if you are a designer and you want to choose materials which can withstand such high heat transfer. With that, we'll stop here.